Hello and welcome back to week 7 of the procedural generation series. So this week I managed to get a lot done. Um, Not as much as I would have liked because I'm still sort of recovering from the schedule shift, but yeah, but I've sort of gotten back on track a little bit. So this week I made a library for the ECS. I've decided to do it externally as a separate library, and it's not in C, it's in C++, though actually I'm thinking of rewriting it to Odin, um, which is interesting. I'm gonna look into that. But anyhow, before we go into this, right? This is gonna be a data-oriented ECS. So what does that mean, right? So I've prepared a little diagram here. Um, so first to review what an ECS is, an ECS consists of three components: entities, components, and systems, right? And the way this works is components are just data structures, right? They have data that you need to actually do stuff, right? Systems operate on components. So systems actually do the thing that you want, right? So there's a physics system that actually makes everything respond to physics, right? And there's a physics component, right, which is called the rigid body usually, and that is responsible for storing the data related to physics, right? So that'd be like the force that's exerted on the object, the velocity, things like that. That'd be what the rigid body stores, right? And then you have entities, and entities are just a group of components. So usually an entity is like an ID, and each component has an ID. So this basically ties a bunch of components to a single entity. That's the idea behind that, right? Because typically in games, what you want to do is you want to get all of the components on an entity. Like you want to get a specific entity's rigid body, right? So you need that association, right? That's the whole point of that. But really, entities don't exist on their own. They're really just a set of components. Um, but yeah, so that's how ECS works. And typically, the way this architecture works is you store the components for data orientation. You need everything to be close together in memory. So that's the first thing. And the second is you need everything to be loaded into the cache. So to do that, you want to minimize the size of your types, and you want to have packed arrays of a specific single type that you're going to use, right? So usually it would be something like this. So let's say, so we would have like arrays usually is the way this is done. This is called like structure of arrays, right? So for the physics system, you'd need multiple arrays. So that's the problem I'm trying to solve here, right? So the first array, let's say this is for the rigid body, right? So because the physics system needs to know the velocity, mass, things like that, it needs those. And it also needs to know the position, right? Which is usually stored on something called a transform, right? So we have two components here at play, rigid bodies and transforms. And the way this works is you store them on two separate arrays, two separate variables, right? But there's a problem with this because in the physics system, let's say we wanted the transforms and the rigid bodies, right? We need all of the transforms and all the rigid bodies, right? If you just loaded both of them into memory, it would look something like this, right? So let's say we have this, right? So let's say this is our cache, right? It would look something like this, right? Let's say the black squares are the transforms, right? So you load in transform 1, transform 2, transform 3, transform 4, right? And then you have rigid body 1, rigid body 2, rigid body 3, rigid body 4, right? And the problem here is you'd be getting data from different parts of memory. So to process entity 1, you need the first transform and the first rigid body, right? But they're not located sequentially in memory. They're located in different locations, right? And this has a problem. Generally, you don't want to jump around in memory like this. You want to operate in sequential regions of memory, right? And for entity 2, you're doing the same thing. You're going to the transform 2 and then rigid body 2, right? So you're sort of jumping around in memory there, right? The optimal way of doing things, I think, is to instead arrange things in a staggered way. So it would be like this. So before we had it like this, now I think it would be best to have it like this, where we have a transform, a rigid body, a transform, a rigid body, transform, rigid body, transform, rigid body, right? And this way the data is accessed sequentially, right? So you're working on entity 1, so you get the transform, and then you get the rigid body, which is located right there, right? Then you're done with entity 1, you go to entity 2 and get its transform and its rigid body, which is right next to entity 1, right? And then entity 3, you do the exact same thing. Entity 4, you do the exact same thing, right? So you're only ever operating on regions of memory that are allocated sequentially, right? And I think this is the optimal cache pattern. This is the optimal data access pattern to follow, right? So that's what I'm currently trying to figure out is how to do this, how to get these two arrays and join them such that you get them like this, right? And this, by the way, is called an equijoin in database terminology. So I'm basically looking for a fast equijoin algorithm. Um, though this is like very speculative, I'm not really sure if this is worth doing even. Like I think it is better data access pattern, but the overhead of the equijoin algorithm might be so great that this is just faster. I need to look into that before I can make a decision. But yeah, regardless, that's like the theoretical stuff I've been working on, right? But as for the practical stuff, I want to, whenever I write code, right, that's based on performance, I want to make sure I'm actually writing something that's performant, right? I want to make sure it's better than like a baseline implementation. So the first thing I did was I wrote just a baseline ECS, right? So this is an object-oriented ECS. It's not at all meant to. This is not at all data-oriented at all, right? This is just like I think a fair ECS, right? This is like a, I think it's like a standard ECS, right? So you have an entity, and the entity has components, right? So this just makes sense object-oriented wise, right? The entity has the components, right? And then you have specific components. You have the graphics component, which is this is just a padding component, really. This is just to see the effect it has on the cache to just have like filler components. And then you have the physics component, and then you have the transform component, right? So yeah, you just have all these components, right? And then on an entity, you just have a bunch of components. And by the way, the components are, these are all subclasses of the component type. This is actually really silly. The reason this has to be this way is, I don't want to recover that. The reason it has to be this way is because I need a base class for the entity, right? Because this needs to be an array of something. It can't be an array of physics components. They have to have base class, even though the base class has no behavior or any reason to exist. But anyhow, right? So we have that. I might be dumb actually. There might be a better way of doing this, but yeah. And also we have systems. So this actually has a base class that makes sense. And this is just an update function. It's a polymorphic function. Um, and the idea is you have different systems and that override this function, right? So I have the physics system right here, which just overrides the function, and then I have the CDP file, and it just does some stuff. It just loads in all the entities, right? It just loops through them, gets all the components, checks to see if we have a physics and transform, right? So we're just looping through all the possible components, and then we're just static casting, doing that, right? I would say this is pretty standard. And then we're checking if they're null. If one or two of them don't exist, we have to continue. Else, we just do some calculation so the compiler doesn't just throw everything away. That's the goal for this, really. And yeah, and that's basically it. And then we have the entry point, and all it does is it instantiates the physics system. I'm storing the systems in arrays because there might be multiple systems that I want to have. So maybe I want to test like what the impact is on invoking like 100 different systems. So maybe just in case, right? I want that. So yeah, we have systems, and then we're just instantiating all the entities, and we're creating all the components, and then this is where the timer actually happens. The timing doesn't take into account the setup or anything, and it's just taking into account the update function of the physics system. So in theory, they should only be capturing in theory, this code should be bottlenecked by cache access. That should be the main thing bottlenecking it. And the primary bottleneck should come from this graphics component because it's sort of getting in the way, right? Yeah, you actually just want physics and transform, but the graphics component is sort of dirtying your cache, right? So in a data-oriented architecture, this would not happen. That graphics component would not be loaded into memory while you're using the physics system. So that's sort of what I want to test, right? So I'm just doing like a basic data-oriented ECS for now, and then I'll look at the equijoin stuff. But yeah, that's all for today's video. Next week, I hope to have more work done on the data-oriented ECS. I just want like a basic implementation, nothing fancy, and then from there we'll see where we go, right? Hopefully, my goal is to beat this implementation by a significant amount. I would say at least an order of magnitude, because otherwise I don't think it's really worth doing. But anyhow, yeah. So I'll see you guys next week for that.